Hello everybody, this is the solution to 3n, Newton's universal law of gravitation. So it says a student is given the following set of orbital data for some of Jupiter's moons and is asked to use the data to determine the mass m sub j of Jupiter. Assume that the orbits of these moons are circular. So they give us the orbital period of some of these moons, so that's how many seconds it takes them to go around, and it gives us the orbital radius in meters of these moons as well. So part A, they say write an algebraic expression for the gravitational force between Jupiter and one of its moons. Well, that's pretty straightforward because Newton's universal law of gravitation say this, that the force of gravity between two objects is the universal gravitational constant, time mass 1, time mass 2, divided by the distance between their centers squared. That's it generically. Let's make it just a bit more specific for this case here. So the force of gravity between these moons will be G. We'll call one of the masses m sub j, and we'll call the other mass m sub m for the mass of the moon there. And then often when they're talking about these radiuses, they make it a capital R, but that doesn't really matter at all. All right, so that's the first part there. So second part, for part B, it says use your expression from part A and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of its orbital radius r. That means we want t to equal something that has r in it. So this one has a bunch of little steps here, so let's be careful. As all of our centripetal problems, we want to start by this, saying the sum of the forces is equal to mass times centripetal acceleration. We know the moon's going in a circle, so we can go ahead and write that. Next step is to write what forces cause it to go in a circle, and it is the force of gravity. And then we can go ahead and write in for what centripetal acceleration is. That is v squared over r. So far I've kept this side generic here, so let's start to plug in for what these things are. This we want to plug in for our force of gravity that we just wrote right here in part A there. So this is going to be gravitational constant, mass of Jupiter times mass of one of the moons divided by the radius between them squared. This is the thing going in the circle, this little generic m here. So this is the moon. The moon is the one going in a circle times v squared over r. So a couple things happen here. So the mass of the moon cancels out, it's on each side. This radius cancels out with one of those radii over there. So let's clean this up a bit, and we've got capital G times the mass of Jupiter over the radius is equal to velocity squared. And that's it, because we've canceled out the r there. So now we got to take a little sort of sidestep here. Let's do velocity. We should be used to this by now. The velocity of anything going in a circle is the distance it travels, let's say the circumference, divided by the time. Let's call that the period to go around once. So let's plug in for here. The circumference will be 2 pi times the radius over the period. And then we can plug this in now for the velocity here. So everything's going to get squared, right? Because the velocity here is squared. So let's do that. So we still have capital G times the mass of Jupiter over the radius is equal to the velocity squared. So the 2 squared becomes a 4. The pi squared is pi squared. The r becomes r squared, and the t becomes t squared there. Be careful about canceling out your r's. One's down in the denominator, one's up in the numerator here. So I'm going to do a couple things then on this next step. I'm going to multiply my t squared up here, and then I'm going to multiply my r up there. So r comes up here, and we actually get r cubed. And then I'm going to divide my g down to the bottom here, and I'm going to divide my mass of Jupiter. So there is the equation right there. Now, if you want actually just the period, then you would take the square root of that whole thing. But I'm actually going to leave it like that because of what's coming up next. So the next thing they say is which quantity should be graphed to yield a straight line, so it's a linearization problem, whose slope could be used to determine the mass of Jupiter. Well, look, they even sort of hint in here. They have seconds squared and meters cubed, so they're telling us basically, I don't know if they intended to do that. I think it's actually a mistake because they tell you to label it later. But anyway, that's useful. So let's take this quantity right here and try and linearize it. So I'm going to do it right here. So let's pretend we leave this on the left-hand side of the equation. Let's pull out all of the constants. 4 pi squared over g times mass of Jupiter. All of those are the constants right there, and then we're going to be multiplying that by radius cubed. So if we do that, this follows a y equals mx plus b, but there's no b format. So this is our y, period squared. This is our x, radius cubed. And all of this right here, 4 pi squared over the universal gravitational constant over the mass of Jupiter, that is our slope in that case. So it says complete the table by calculating the two quantities to be graphed, period squared and r cubed. Label the top of each column, including units. Well, they actually included the units for us. They already did it. So here, I went ahead and filled it out so you don't have to watch me solving this. So all this column here this is the period squared. I will label that. And so I went ahead and took all of these periods here and I squared them. And then this column right here, they gave you a hint, meters cubed. This is the radius cubed. So I went ahead and took all the radii here and I cubed them. So now they want you to graph this in part E. So I went ahead and did that, and you should get something that looks a little bit like this. So notice they went ahead, and also, if you looked at it, they gave you the hint here. Here's period squared right there, and there's radius cubed. So if you didn't know what to do, they basically told you. So I went ahead and plotted these points. I don't know if you can see them. There's one here, 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 and here. So there are the 4 points. And then I went ahead and put a line of best fit through there. So they never actually tell you to find this slope. But here, for a Hostess cupcake or equivalent, I'm going to offer this challenge to see if anyone's actually watching this video. So again, make this graph, get your slope. Notice what the slope is equal to. The slope is equal to this. You know 4 and pi, those are just numbers. G, you already know. So you should be able, if you have the slope, to find the mass of Jupiter. So you come to me, show the work, and I'll give you a Hostess cupcake or equivalent for that. Remember that when you go to find the slope, you don't want to pick points that are data points if they're not on the line. So that would not be a good point to pick right there. This one's okay, it's right on the line. It's nice to pick ones right where it crosses an easy point, although I don't see a bunch here. It looks basically like right there. But anyway, you want to pick lines that are on your line of best fit. All right, one more thing we got to do here, which is part F. So it says 2 identical probes are sent to study one of Jupiter's moon. Probe A is in a geosynchronous orbit around the moon. Let's draw a little picture of that. So here's the moon right here, and A is floating out here in space, and it's floating around around the moon like that. Probe B rests on the surface, so there's B right there sitting on the moon. And rotates with the moon. Rank the magnitudes of the following gravitational forces from greatest to least. If 2 or more quantities are the same, say so clearly. So let's start to look at these. The force of the moon on probe A. I think I can see where this is going, right? Let's find a Newton's third law pair. The force of probe A on the moon. Those two must be the same according to Newton's third law. So I know that A and C must be equal to each other. The force of the moon on probe B and the force of probe B on the moon. Likewise, those two must be the same. So B must equal to D. It is there. And then down here they have the force of probe A on probe B and the force of probe B on probe A. So also according to Newton's third law, E must equal F there. Now let's put all of these together. So who is going to be the strongest? Well, here, B and the moon are closer together. So according to the gravitational equation, the smaller your distance is, the bigger the gravitational force. So those two should be the biggest. So let's write that. B which is equal to D, will be bigger than any of the other ones. Then the moon's pretty big still, so it's going to pull on A, but less. So that force is going to be greater than it pulls on probe A, because probe A is a bigger distance away. So A then would be less, but that's got to be equal to C. Now what about these two on each other? Well, they're the same distance away as the A and the moon is, but B has a teensy mass. That pull's going to be nothing. So that one's got to be last, the gravitational force that the two probes pull on each other. So then finally, E's got to be equal to F.